Greetings. I, Chankiki, will be presenting on my FYP topic, SERS-based biosensing with noble metal nanoparticles for application in virus detection. The world was plagued by 3 coronavirus outbreaks in the last 2 decades: SARS-CoV-1 in 2003, MERS-CoV in 2012, and SARS-CoV-2 in 2019. As made apparent by our own individual experience of the COVID-19 pandemic that is still ongoing, one of the major factors contributing to the situation was the lack of affordable and quick testing. This showed how a relatively cheap, quick and accurate testing or monitoring device could be crucial in the future as a solid line of defense in identifying, studying and preventing an unknown unseen opponent such as SARS-CoV-2. All this brought attention to the advantages of surface-enhanced Raman scattering, or SERS, technologies, which stood a contrast to the limitation of current conventional testing methods, such as RT-PCR, which prompt further examination into the utilization of SERS in detection of virus particles. Summarize and review recent advancement in trends of SERS-based biosensing strategies for virus detection, including their strengths and limitations. Assess the factors affecting the diagnostic performance of SERS in regards to virus biosensing. Highlight prospects and present challenges in SERS and biosensing technologies. This review could serve as a quick overview to developing future strategies in outbreak prevention and management and aid in the advancement of SERS-based viral sensing devices. The emergence of a dangerous novel strain of infectious virus is not a matter of if, but when, and a significant number of existing virus particles detection methods face many limitations that restrict the practical use of these methods, particularly in rapid diagnosis of mass population to contain the spread of a virus that is facing constant rapid mutation. Early diagnosis of many severe infectious viral diseases such as mosquito-borne diseases is critical but challenging because biomarkers are present in low concentration, demanding bioanalytical techniques that can deliver high sensitivity with ensured specificity. Both SERS and biosensing are both relatively new to the game of human technology. Much is still left to be explored. Many questions are still left unanswered. Therefore, more research needs to be done. First reported by C.V. Raman in 1928, it is an inelastic scattering phenomenon of light that probes molecular vibrations to provide a molecular fingerprint of materials. It is fast, cheap and non-destructive spectroscopic technique, with flaws a later discovery paved way to rectify. Surface-enhanced Raman scattering, or SERS, was coined after a study found pyridine adsorbed on a silver electrode experienced considerable Raman scattering enhancement. SERS is a phenomenon when an analyte is adsorbed onto a closed tool of a metal surface, or plasmonic nanomaterial. Together with excitation laser produces surface plasmons, or coherent electron oscillations, which significantly enhance Raman signals. In context of SERS, plasmonic nanomaterials are referred to as SERS substrate. Noble metals, namely gold and silver, are commonly used due to their higher enhancement factors and availability of plasmonic resonances in visible or near-infrared regions. SERS-based biosensors are analytical devices in which biological recognition molecules such as enzymes, antibodies, or nucleic acids are coupled with an optical transducer, or SERS substrate, that a detector then detects the interacted analyte, producing digital outputs. SERS-based detection of viruses follow 2 formats. The direct detection format involves the adsorption of an analyte or the presence of an analyte in close proximity to the SERS substrate, which allows for identification and quantification based on the analyte's own unique SERS spectral fingerprint, without need for a reporter molecule. Direct SERS have been utilized in many studies and were found to have formidable diagnostic sensitivity and specificity, time of analysis being the main advantage over PCR, which took 4 hours, while many of the direct SERS schemes employed only took approximately 10 minutes per sample. The development in statistic methods of spectral analysis has also made distinguishing SERS spectra of different strains of the same virus possible. The results suggested that SERS permits rapid and accurate virus identification, including differentiation of a single pathogen at strain level. The biggest disadvantages include inability to determine virus titer, sensing in biofluids could result in spectra that are difficult to interpret, spectral bands could overlap, causing difficulty in discrimination of target. In indirect SERS-based techniques, specificity is provided by molecular recognition elements such as antibodies, aptamers, or other special binding molecules immobilized on the surface of sensors, which selectively capture analytes molecules, placing them close to the hotspots on the surface. The SERS signal comes from a Raman reporter molecule, not from the analyte itself. With indirect format, multiplex detection can be achieved. It allows for measurement of SERS spectrum changes of a metabolite, reaction product, or reporter molecule with concentration of target analyte. Spectral interference from sample metrics is minimal as molecular recognition elements are used. The main disadvantage of using this detection mode is molecular information of the analyte itself cannot be acquired. The molecular recognition element and reporter molecule of this mode have to be chosen with great care, because it could affect the enhancement factor. Two key components affecting the diagnostic performance of SERS-based biosensors are the optical transducer and molecular functional interface. The optical properties of a SERS substrate affect the analytical sensitivity, while the functional interface of a biosensor determines the detection specificity. A great deal of work has been done in designing different types of plasmonic nanoscale substrates. The LSPR and magnitude of SERS enhancement can be modulated by changing the size, composition, shape, and the local environment of the nanoparticle. The type of nanoparticle assemblies, such as two-dimensional or three-dimensional stacking, could also influence the plasmonic hotspots, controlling the SERS enhancement factor and even passive analyte trapping capability. Two main factors are to be considered when designing the functional interface: that is, stability of the substrate in biological matrix and molecular recognition moieties for biomarkers capture. Capping ligands could be employed to maintain colloidal stability. The physical distance between the transducer and analyte should be kept at optimum to obtain higher SERS signal enhancement. As the fields of advanced material science and nanomedicine are still at its infancy, I am highly confident that with further research and development, the combination of SERS and biosensors could potentially be the future formula for promising breakthroughs in the realm of healthcare and nanobiotechnology.